Hello everyone, we're gonna do question 11 out of the series of the revision summary sheet with 32 questions that we were doing. And question 11 says explain the difference between mass and weight and what units are they measured in. So I'm gonna write mass here and weight here. And I'm going to do a little sort of comparison table, which is always nice and fast to do. So differences between mass and weight. The first one is that mass is a scalar, and hopefully you know what that is, and weight is a vector. Just to refresh your memory, a scalar has, let me just close Skype, which is annoying. Yes. Okay, so a scalar has doesn't need a direction, but a vector needs a direction. And this is on top of obviously the magnitude, which they both have. Magnitude or size, they both have. Scalars and vectors are both types of magnitudes, types of size, but the vector has a type of a quantity which is also, apart from magnitude and size, has a direction. So weight being a force, it's a type of force, it's a vector, it's got a direction, so it's a force, and mass is just a quantity. Okay, and what's the meaning of each one? Mass is the amount of stuff, otherwise known as matter, and the weight is the force exerted by the earth, by the gravitational field of the earth on the stuff. Right? So hopefully that makes sense. And the units of mass are obviously kilograms, and the units of weight are newtons, right? And if you want to go from one to the other, you use this formula here, which says that weight is equal to your mass times g, where g is a gravitational constant for the earth, otherwise known as 10 meters per second squared. Right, so if you get your mass and you multiply it by 10 meters per second squared, then you get weight, which is in newtons, mass is in kilograms, and acceleration, this is in meters per second squared, which is acceleration. So this looks like, look, newtons, that's a force, and that's kilograms, that's mass, and that's acceleration. So this famous second law of Newton, F equals ma, is really where this kind of formula, weight equals mass times acceleration, comes from. And next year we'll be doing a slightly more complete expression for what the weight of something really is, or the gravitational force of attraction, which is universal and will be true for the moon and the sun and their attraction between them and the earth as much as it is for us, our bodies here on the planet. So hopefully that answers that question on the difference between mass and weight. One of them is a force and the other one is just a quantity. That was question 11. So when you do these questions, more than just trying to answer it quickly and just saying, hey, this one is this and the other one is that and this is the unit, the best thing is to really try to explore the idea a little bit like this and make yourself some notes as you go, and make it a little bit more full than you would if you were just trying to get out of the way, because that's what really revision is about. It's about going a little bit deeper than you do when you visit these ideas the first time, and that way they'll hopefully stay in a little bit better. Okay, so I've just deleted that part and opened a new blank space to do the next question. I'm also saving the images, and I'll send you the images out in case anytime you want to go back to one of the sort of Blackboard writings without going through the whole video. Then you'll have the images also. Okay. Question 12 says, what is the formula for weight? So we just answered that without knowing it. We had that weight is equal to the mass times the gravitational acceleration g, and it says illustrated with an example of your own. Well, I'll do it with my own example. My mass is approximately equal to 95 kilograms. I know I need to go to the gym, and the gravitational acceleration g is roughly around 10 meters per second squared. And so if we want to find the weight, which would be what's the meaning of weight? It's the force exerted by the planet's gravitational field on a mass, right? So that would be 95 times 10, and that would be roughly 950 newtons, right? I say roughly because this is not really 10. Gravity is closer to 9.81 something, but in GCSE we're going to be using that, which just makes things a little bit easier. And so that would be the weight, the force acted on me by the Earth. And just worth mentioning here, if you remember Newton's third law, you'll know that every force has equal and opposite counterforce. That's the third law, and it's they act on different objects. They act on different objects. So that means if I am pushing with my hands, if this is me and I'm standing sideways and I'm pushing with my hand on the wall, then this is the wall. Then if I'm pushing with 40 newtons of force on the wall, then the wall is pushing on me, right? This is my hand on wall force, and this is the wall on hand force. They're both equal, right? Those two are equal. That's why I'm not going through the wall and the wall is not going through me. That would be harder, but I'm mobile, so I in theory could move through the wall if the wall wasn't able to provide that same force against me. And so if I'm there in equilibrium against the wall with this amount of force, then that's how much force the wall is doing against my hand, right? So they act on different objects means one of the forces acts on the wall and the other one wow, this was wall on hand, and the other force acts on the hand, and they're equal in magnitude and opposite in direction. So here, if I just calculated the amount of force that the planet is doing on my body, then that's how much force I'm also attracting and pulling on the Earth, right? It's just that when I jump, you can see me accelerate really quickly down again, and the planet doesn't look like it's moving very much because the mass of the planet is that big and mine is something like that. So because both forces are the same, then MA for the planet means a very small a, but for me it's a very small mass, so it's a big A. But they're both equal. That force and that force are equal and opposite. So that's just a little recap on Newton's third law and weight, and we're gonna now go on to question 13. Write down Newton's first law of motion and illustrate it with a diagram. So we were talking about the third law here, so let's talk a little bit about the first law of motion. We're gonna do it in yellow, why not? So Newton's, sorry, let me just put the number of the question down, 13. Newton's first law of motion. The way I like thinking about this law is this, the velocity of an object will remain unchanged if no unbalanced forces act on it. Or another way of saying it is the velocity of an object will remain unchanged unless an unbalanced force acts on it. Same thing. So this velocity, note that that velocity doesn't have to necessarily be bigger than 0. It could be 0. Right? So always have this in mind. If something is stationary, just sitting there, then its velocity is not going to change unless somebody comes and puts a force on it, or unless you make a hole here and then gravity can act. If you make a big hole there, or something like that. So there needs to be a force on that for its velocity to change. Otherwise, if it's already moving, it's going to continue moving at the same speed. If this is frictionless, if this was some kind of frictionless ice, this is just going to keep on moving forever and ever and ever unless a force acts on it to stop it, if it's already moving, if it's got an initial velocity v. Right? And note that the word is velocity, and velocity is a vector. So if this is going in a straight line, it's not suddenly, if this is going like that and we're looking at it from on top, it's not suddenly gonna turn like that, because that counts as an acceleration. The velocity here is changing. The speed could be the same, but the velocity suddenly changes because the direction changes, and for that to happen there would have to be an unbalanced force acting also on it. So hopefully that makes sense. And it asks us for a diagram also. So well, here we have a kind of a diagram, and I could write velocity unchanged unless unbalanced force. Why do I keep saying unbalanced? Because if two forces act on this and they're equal, one of 5 newtons is acting on it and the other one is 5 newtons acting on it also, they cancel each other out and they don't make any difference to the movement of this. It won't speed it up, it won't slow it down, it won't start it moving, it won't do anything at all, so we might as well ignore them. So they need to be unbalanced, right? There needs to be here maybe 3 newtons trying to push it forwards. Maybe the friction is bigger for some reason than 3 newtons. Maybe it's 7 newtons. And then there will be 4 newtons extra going backwards. So if this is already moving with a velocity, it will start to slow down because the backward force is bigger than the forward force, so then the velocity will change. But otherwise, if there is no unbalanced force, it will just keep on going at the same velocity forever. Even if it's going at 0 velocity, it will also keep going forever at 0 velocity. So we're nearly running out of time, but I wanted to mention briefly that this is a really important law. It sounds like a bit obvious because, okay, if no unbalanced forces are acting on something, then obviously they're not going to change the velocity. But Newton didn't know about gravity, right? So if he was just looking at a block like that, and it or a leaf on a tree, on a branch of a tree, I'm not going to try to draw a tree, but that's a, I don't know what that is. But I don't know, if this is a leaf like that on a tree and it just suddenly falls, then he must have known about gravity or discovered it at the same time as this, because he must have known there's a force there acting to change it. Hopefully that makes sense, and we've just run out of time. See you in the next video.